Good evening. I'm deeply honored having opportunity to present today. My name is Jae-won and I'm affiliated with Catholic University of Korea College of Medicine in Seoul. The topic of my presentation is the clinical efficacy of powered robotic lower limb exoskeletons for rehabilitation. The recent advancements in technology are truly remarkable. Observing the movement of Watson Robotics Atlas, you can see the core technologies in the field of rehabilitation robotics have already reached a high advanced stage. The key issues now lies in how to effectively apply this advanced technology to clinical practice. Various types of robots such as Locomet or Newark or other many robots are already commercially available and in use. Before proceeding with my presentation, please allow me briefly introduce myself. As I mentioned earlier, I work at Yeouido St. Mary Hospital, which ranked in 170th in Newsweek Global Hospital ranking. And Yeouido St. Mary Hospital is one of 8 affiliated hospitals in the Catholic Medical Center. And the Catholic Medical Center is the largest single healthcare institution in South Korea, with approximately 10% of all interns and residents in the country receiving their training at our institution. This is a map of Seoul, and among the 8 affiliated hospitals of the Catholic Medical Center, 3 are located within Seoul City. Yeouido St. Mary Hospital is located on Yeouido Island, which lies within Han River, and Yeouido is one of the most bustling areas in Seoul and is also home to the National Assembly. And I'm a professor in my university and head of the Department of Rehabilitation Medicine in my hospital, and serve as director of the Korean Academy of Rehabilitation Medicine. And additionally, I contribute as a section editor for the official academic journal of Korean Academy of Rehabilitation Medicine. I am truly delighted to have this opportunity to present today. I sincerely hope that this will pave the way for building meaningful network in the future. Let us return to the main topic. This is a rehabilitation treatment guideline for children with cerebral palsy, published in DMCN in 2013. It has long been recognized that goal-directed training plays a critical role in rehabilitation therapy, and it is on the top of the list. In the early 2010s, robotic therapy was considered a part of assist technology, and its recommendation level was not particularly high. In the updated version published in 2020, there are no significant changes. However, with advancement in technology, you can see that the term robotics has been explicitly mentioned. As mentioned earlier, the key principle of rehabilitation medicine is task-specific and goal-directed training, and the training improves specific movement being practiced. Considering that muscle activation patterns in actual walking are clearly different from those in treadmill walking, it becomes evident that our ultimate focus should be on overall ground walking. Furthermore, restoring walking ability is very important. This study reports the relationship between the average daily step count and annual mortality rates, showing a dramatic decrease in mortality rate as the average daily step count increases. This means walking is indeed crucial. However, in actual clinical practice, it is challenging for caregivers to physically support patients and helping them work. In this regard, exoskeletal robot can help rehabilitation and caregivers. Among various types of lower limb exoskeleton, overground type is designed for walking on the ground, mimicking natural walking in real-life environment. It provides realistic and natural gait training and improves mobility and independence. Treadmill type utilize a treadmill where a user practices walking with robotic assistance in a controlled environment. As advantages, it allows repetitive and stable training in a fixed space and facilitates load adjustment and gait pattern analysis. Also, it can include safety measures like a harness to prevent falls. In the end effector type, the robot is directly attached to the user's feet, guiding them through precise gait trajectories. Usually, it has a simple design and easy maintenance, and it enables precise control of walking patterns. Among the various types of rehabilitation robots, I have believed for over a decade that the overground type would be better for lower limb rehabilitation robots. Accordingly, in 2017, I used the EXOWork, followed by the SUBA from 2018 to 2020. And nowadays, starting in 2024, I have been using the EA2 Pro. As you can see, while their form differs slightly, they share the common feature of enabling overground gait training. The research demonstrating the effectiveness of robot-assisted gait training has been consistently reported since the late 2010s. This study from Japan reports the positive outcome of approximately 20 training sessions using the HAL system in subacute stroke patients. This study conducted in South Korea using EXOWork. This research involved 20 sessions of 30-minute training and reported slightly better outcomes compared to conventional treatment. As shown in the image, the EXOWork does not provide trunk support. Consequently, it cannot be used in the patient without a certain degree of trunk control. For this reason, this study was limited to patients who can stand alone. There is also research utilizing the EA series of Cosmo Robotics. This study was conducted at Korean University Hospital in South Korea. Similar to previous studies, 30-minute training were performed with a total of 12 sessions. The results showed significant improvement compared with conventional gait training by physical therapists. According to a recent systematic review published in 2024, robot-assisted gait training (RAGT) have a potential role in the recovery of walking dysfunction after stroke. However, when compared to conventional therapy, the differences are not substantial, indicating the need for further research to determine which treatment is superior. The interesting point is that, as I thought in the early 2010s, overground type are showing significant improving in the walking performance, and it looks like overground type may be superior to treadmill type. Including the EA2 Pro, overground robot-assisted gait training are more closely resemble actual walking, as it allows walking forward. In subacute stroke patients, it is common to encounter patients whose trunk control is compromised, so it would be ideal if it includes a trunk support option. And when applying robotic systems, it is also essential to check for joint range of motion limitation or excessive spasticity to prevent the patient injury. What could be the mechanism behind the positive outcome of overground type robot-assisted gait training? I believe there are three mechanisms at play. First, it aligns well with the rehabilitation principle of task-specific training. When you practice, the specific movement you practice improves. Second, it improves cardiovascular fitness. In rehabilitation therapy, even maintaining a standing posture can yield a positive effect. Third, patients tend to find it more enjoyable and are more likely to actively participate in the therapy. Rehabilitation robots often make patients stand for 20 to 30 minutes, which can be more tiring than expected. This is something to watch out for, especially with subacute stroke patients, because it can cause syncope or hypotension. What is clear is that robot-assisted gait training goes beyond the simple effect of tilting, and it can offer the next level of rehabilitation. During the past 10 years of applying robotic therapy, I have 2 cases of patient syncope. Both incidents occurs in elderly people with subacute stroke. Except those, these type of robot therapy are effective and safe tools for rehabilitation. In some cases, therapists have to continuously support the patient, which can be more physically demanding than expected. So, what will the future of powered robotic lower limb exoskeleton look like? Since the technology is already well developed, the key will be how this technology can be integrated with other fields. In my opinion, the first is the integration with AI. This study was published by our research team in 2020. We processed the biodata with AI to simulate instructions similar to those given by therapists to patients. We selected 6 common instructions given by therapists and trained the AI to understand the situation in which these instructions are typically made. As a result, we are able to develop an AI system that delivers instruction with nearly 90% of similarity to those provided by actual therapists.
아주 잘하고 있습니다.
아주 잘하고 있습니다 means great.
상체 세우세요.
상체 세우세요 means pull up your trunk.
오른쪽 다리 긴장 푸세요.
오른쪽 다리 긴장 푸세요 means relax your right leg.
아주 잘하고 있습니다.
That means great.
아주 잘하고 있습니다.
So we give positive feedback to the patient. At the end of therapy session, the AI generates a report on performance metrics such as bug balance tests and so on, which based on the therapy data. And this system improves the compliance of patient, and also this kind of system has the potential to be expanded for the use in telemedicine. This is another paper related to AI published in our research team in 2021. How intensely should we apply rehabilitation robot? Patients may require training at various levels of complexity, ranging from standing practice on tilted table to more advanced tasks such as climbing stairs. What type of training should be prescribed? As briefly mentioned earlier, particularly in subacute stroke patients, unstable vital signs can pose challenges during robotic therapy. Prescribe appropriate exercise is a key concern for many physicians. Our research team utilized various measures such as a functional scale like modified Vassell index and functional ambulatory category, as well as blood chemistry results including CRP, cholesterol, and lymphocyte level, and so on, to propose the most suitable AI model for determining the appropriate level of exercise. Second is integration with functional electrical stimulation. This paper published in the New England Journal of Medicine in 2018 caused quite a sensation in the academic community. I also personally found very interesting to read. In fact, this system operates in a classical manner, not by moving the legs through the individual muscle controlled by electrical stimulation, but by increasing sensory input to induce motor output. As you may know, motor control in the spinal cord is determined by the amount of input that reaches motor neurons. Our nervous system functions as a sort of biocomputer, processing sensory input and generating appropriate motor output. As in this study, increasing sensory input through electrical stimulation and generating meaningful motor output from it requires an intact spinal circuit. This mechanism is also why the study focused on specifically individuals with high spinal cord injury between the C4 and T4 level. This study is one I published last year. I conducted the research out of curiosity about how much output could be elicited from individual muscle using electrical stimulation. The results showed that the muscle output achievable through electrical stimulation was about 20% of maximal voluntary contraction. Therefore, I anticipate that in the future, the remaining 80% will be compensated by exoskeletal robot, and AI will be integrated into the system. In summary, robot-assisted training might have a potential role in the recovery of walking dysfunction after stroke, and also in spinal cord injury. Especially overground RAGT may be superior to treadmill RAGT. Considering the pace of technological advancement, the future of RAGT is promising, with expectation for integration with various fields such as AI and FES. In 2018, I spent a year as a visiting professor at Stanford University. More recently, I have had the opportunity to collaborate in workshops with professors from Johns Hopkins Hospital and Mount Sinai Hospital in New York and Mountain View Hospital in Las Vegas. I sincerely hope to continue connecting with many physicians who share an interest with rehabilitation robotics. Thank you for listening. Wishing you a wonderful new year. Dhanyavad.